go. Hello, Mr. Harry, Mr. Ryan, are you right? Yeah, okay. Okay, so we have talked about the tree detection algorithm for 3 days, okay? So for 2 days actually. We talk about depth search, we talk about breadth search. So basically we're given this graph and left and right, representing the left child and right child of the node I, right? Node I is from 0 to n minus 1. And we want to find out if this given graph is a tree, right? It's a tree. It's basically a binary tree because there is only left and right array, okay? So in order for a graph to be a tree, so what makes it a tree?
So small.
So what makes it a tree? So what are we looking for? Connected, yes.
No cycles.
No cycle, connected, yeah. So we want to find out the root. The root is the node.
Unacceptable.
Yeah. The root is the only node that has the 0 in degree, okay? Has a 0 in degree, okay? So if we have more than one node that has 0 in degree, then that is not connected, right? So it could be something like this, right? This is, we have 2 nodes.
Look at my mini phone.
Okay. We have 2 nodes. Look at this one. Is this a tree? Is this a tree?
No.
Yeah, why is that?
It's not connected. No numbers.
Yeah, okay. It's disconnected, right? It's disconnected. We have 2 roots. We have 2 nodes with 0 in degree. Okay, let's stop. And how about this? Is this
No.
tree? No?
No numbers and it has a cycle.
No, okay, it has cycles, okay? Don't worry about the numbers, okay? Okay. And how about this? This is a tricky one. How about this one? Is this a node? 1, 2, 3.
No.
Why is that? Yes?
Because it has 2 roots.
Well done. Yes, 2 roots. Yes. Why? It's connected, but it has 2 roots. But this one is a special. It's a case that it shows that one node has 2 parents. But in a tree, what do we have? How many maximum parents can a node have in the binary tree?
2.
The parent, not
1.
kids. 1, yes. 1 exactly. Okay, 1 exactly. Okay, come on. Okay, so now oh my God! So, okay, that's it. Okay. So we talk about the depth search, yeah, and breadth search. Okay. Everyone, come and sit down, please. Here, this is counting the in degree, right?
Look at my cool skills.
Right, we're counting the in degree. If a node has more than 1 in degree, so what happens? If a node has more than 1 in degree, then it's not a root, right? Obviously. And then we are finding the root, and then we do this breadth search or depth search. We want to make sure that each node can be visited exactly once from the root, okay? And then at the end we check that the node visited is exactly n nodes, right? N nodes, okay? So today we want to talk about the same problem, but we want to find out. We want to use another algorithm, which is called the disjoint set. Yeah, you remember this?
It's
Yeah.
a coin set.
Disjoint set.
It's always
And
destroying.
union find disjoint set. Okay.
Destroy set.
Disjoint set.
Destroy set.
Okay, so
Dun, 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 dun.
come on, guys. Come on. Too much.
Yeah.
Too much. Okay, what happened to this? This is not working as expected. This is too much. Okay. Oh my God, this is not very useful, right? It's not very useful. Can I have some of these, okay? Some of these.
Not very, very useful. Well.
Okay, come on, guys. Okay, come on, guys. Put it on. Okay.
Yo!
Okay, like disjoint set, yeah? Disjoint set. So, how do we apply this disjoint set and unify? Remember, disjoint set, we have this, at the beginning we have n group, yeah? N group. And then we can have a function operation to union. So we can union 2 into 1 group, or union another 3 into 1 group. And then at the end, if it's a tree, how many groups do we have? If we look at the beginning, we have n nodes, but a tree, for a tree, you say it's connected. How many groups are there? How many groups? 1. Yeah, exactly. How many? Yeah, exactly. So we can use this union find disjoint set to solve this problem. But okay, so let's do this union find again. Okay.
Destroy set.
Okay, let's see. Too much, Eric. Right, too much. Too much. So disjoint set. I just need a better pen. Okay. Okay, so first of all, disjoint set. Let's say class disjoint set ds. Okay, ds object. So define init
Prof.
self n. How's that? Oh, it means that we have n at the beginning. We initialize as n group. Okay, so let's say n group. So how to do the n group? Self dot par stands for parent. Yeah, parent equals at the beginning. You'll be n group will be. So at the beginning, you'll be initialized to from 0 to n minus 1. So we can turn this and this kind of range n is a range n is an iterator that will give us the from 0 to n minus 1 and convert it to a list that fits perfectly this purpose. Okay, and then self to parent. Okay, so we want to have find what? Find x. We want to find the parent of x. Okay, we want to find the parent x. Remember, if it's not the parent of x, so look, if self dot pair x not equal x, yeah? If it's equal as x, then it's a group. And then what do we do? Then we do this self dot pair x equals self dot find recursively calling it, yeah, self dot pair x. Okay, so I'm gonna put this here. Okay, and then we just return self dot pair x. Okay, so what does it mean? Okay, so look, this is to compress the path. Okay, compress the path. Self dot parent. If the second parent x is not equal x, if this is not a group, then we need to keep finding its parent. Okay,
Yeah.
keep finding its parent. Okay, this is the find, and then how about define union? Yeah, union will merge two groups together. So this is a little bit more work to do here. Okay, I'm gonna write it here. Come on, guys, sit down, please. Listen.
Okay.
So first of all, the parent group is of x equals self dot find. Yeah, we use this find function x, and then py equals self dot find y. Okay, so look, we want to merge x and y, but if they belong to the same group, we don't need to do anything, right? Right? If they already belong to the same group, like if px equals py, right? If vx equals py, return. Okay. Okay. For now, I'm just going to merge for x to y or for y to x. It doesn't matter. Okay. So let's do this self dot pair px equal py. Okay. So once we have merged it, so we have one more less component, right? At the beginning, okay, Eric. At the beginning, we have n group, and if we merge two groups, how many groups left? How many groups left? Come on, very easy question. I have n group, and then I have merged two nodes. How many groups are there?
N minus 1.
Well done. That's exactly what we're looking for. Okay. So at the beginning we can put another one. Self dot size equals n group, right? And then we are merging one. So self dot size minus equal 1, right? Here, right? So the thing here is that remember the disjoint set. There are two groups. Okay, here. So you tell me which group merge to which group is better. Here, look. Okay, everyone, look. Guess. We'll talk about this. I have a group, bigger group. I have a smaller group. So is it better to attach the bigger group to the smaller group, or from the smaller group to bigger group? Which one do you think is better?
Bigger group to smaller group.
Smaller group to bigger group, right? That's better. Why is that?
Because you only because there are
Let's try. Yeah, it's quite close to what, but it's not exactly do less, but it's that because the total path. Yeah, if you attach more to here, and then the total path will be more. But if you attach less to more, then the total path will be less. Right? So something like that, right? So in order to do that, we're going to do this sizes. Okay, sizes equal at the beginning 1 times n, right? And then too much noise. Okay. Union. In here, union. So in here, union. I'm going to check, right? If I'm going to check what? I'm going to check here. If the sizes self.size is px, if it's smaller than py, then I swap px and py. So the thing is, I want to append the group with less to the right, to the bigger one. So if after swap the px is bigger, right? If it's bigger, then I can say I want to move the py, attach py to px. Then I can say self.size is, so size is px plus equal self.size py, right? And then I can set self.parent py equal to px, right? Okay. So this is one of the things. Okay, so with this is the disjoint set we have talked about a long time ago. Okay, this is one of the data structure that is useful to do this kind of thing. What kind of thing? So you can merge. It's a graph data structure. You can merge different components, and then at last we can check how many components, how many groups left. Okay, so we can have this another property. At property define count, and then I will return which parameter is it? Self.sizes. Okay, self.sizes. Return self.sizes. Right. Okay. So now I'm going to write the main thing. Okay, which is I'm going to write the main thing. This is the wipe for the babies. It's not very good for wiping the whiteboard.
You need to get a whiteboard wipper.
Yeah. Okay, so the thing is how do we apply this disjoint set union find into solving this problem to find out if a graph is a tree? So basically it's actually a lot easier, yeah? So normally we don't have to implement the disjoint set. You can just import it, or maybe, we don't really have to reinvent the wheel every time. So define, this is tree detection, okay? This comes the magic, yeah? It's actually very simple with the disjoint set. The left, the right? So okay, ds equals n equals length of the left. This is the n equals length of the left. Also, length of the right is the number of nodes of the graph or a binary tree. Okay, ds equals ds n. Okay, then right for I'm going to iterate. the node I in range n. Right. So let's say if left I not equals -1, right? If the node I has a left node, right? Look, this is I, right? Look, this is I. If I have a left node, which is left I, right? Yeah. Then what do we do? If we have an edge coming from I to left I, what do we need to do? We don't need to use the disjoint set to merge it. Yeah? So look, if there's an edge coming from the node I to left I, what does it mean? These two belongs to the same group, right?
Yeah.
So what do we do? Look, ds dot union. Okay, then now we have to do this. ds union, not union. I left I. Then we return false, right? Return false. Okay, so I think we forgot about in what cases we need to return union. Remember the ds to union. If it's the same group, then we return false, right? If px equal py, then we return false, right? Return false. Otherwise, do the merging, return true. right? So if these two nodes already belongs to the same group, then we return false. Everyone, make sense? Why is that? Look, there might be another edge coming later, coming back. Then this will return false, right? So that's what I mean. And the same thing here. If right I not equal -1, and if not ds dot union I right I, yeah, we want to merge the node with the right tree, return false. Okay, so look, there's a right I. Okay, I'm running out of this ink, this one. Right, so here. Okay, so this is all okay for most. Okay, but it's a special case. This does not detect. Why is that? Look, the one I'll show you to Ryan before. Look, if this node 1 points to 2, and another node 3 points to 2, it does not violate this condition. Look, we just merge it, right? So it's the same group. It doesn't matter. How do we check this? This is not allowed, right? Because look, this two has 2 parents, so we can use the integrate. If
I
this
have
number
2
2,
parents.
yeah.
My mommy and my daddy.
Okay. But in binary tree, in data science, in data structure, a node can only have 1 parent. Okay. Yeah. So this is the binary. This is a tree. This is a tree. Okay. So this is a tree. A node can only have 1 parent, right? Okay. The node can only have 1 parent. If another node comes in, this is invalid. This is not a tree, right? It's all good graph actually. So we want to find out this kind of thing. So we use the integrate. Yeah, integrate. Let's say in int equals default dictionary int, right? So we just do this here. So left. Okay. So if left I not equals 1, then data the integrate left I plus equal 1. Then we have to check if this is bigger than 1, we return false. And at the end, if all these tests pass, then we return true. Okay. Yeah. So to sum up, how do we check if this is a tree? Okay, let's just forget about coding. Let's just walk through the examples, a few examples. Okay, and then we find out. Okay, not return true. Actually, it needs to return the size needs to be 1, yeah, because only 1 component, right? Yeah. Look. Okay. 1, 2, 3, 4. Okay. This is not a tree, yeah. Look, it's disconnected. Yeah. How do we use this? The ds at the beginning, 1 to 2. Yeah. So 1 and 2 merge to 1. 1, 3 and 4. Merge to 1. How many size? When the ds dot size, they will return 2 because there are 2 groups, right? Everyone look. Then it's not equal 1, then return false. How about this one? 1, 2, 3, 4. Okay, it's actually there's a cycle. Look, 1, 2, 3. Yeah. So 1 to 2. So I have 1, 2, 3 here. Okay, look at 1 to 2. So these 2, same group. 2 and 3. Okay, I include one more 1. Yeah, look, 3 and 1. Look, 3 and 1 already in 1 group, so it returns false. Right here. And how about these cases? 1, 2, 3. Okay, look here. This one. Yeah, the last example. Look.
Yeah.
This is one. This one. Ready? Look, this one. 1, 2, 3. 1 to 2, 3 to 2, it's okay. But it violates the integrate because integrate 2 has more than 1. Right? It means it has 2 parents. That's not right. Okay? So the second one, yeah. So basically this disjoint set helps to find out if there's a cycle. It's very good. Helps to find out if it's disjoint. If it's disconnected, because at the end we will find out if ds dot size if it equals 1. But for these cases, we need to use the integrate, right? A node A note in a tree cannot have more than one parent. Okay? It's a note in a tree. There's a note in a tree that does not have any parent. What is it? Well done. You're listening. Well done. Good job. How many kids? I mean, the kids, the note which does not have any kids. What do we call them? Leaves. Yeah, exactly. Okay. Yeah. That will be it for today. Bye bye.
Bye.
Bye bye.